Today I'll be talking about fructose metabolism and hereditary fructose intolerance. The purpose of this video is to describe the normal pathway of fructose metabolism and then use this information to show the metabolic disturbance in hereditary fructose intolerance and its biochemical consequences. First off, fructose is a monosaccharide that is widely found in nature in fruits, vegetables, and honey. It can be ingested as free fructose or come from sucrose, which is digested by the brush border enzyme sucrase to form one unit each of glucose and fructose. It is then absorbed across the small intestinal enterocytes in a process that is facilitated by the GLUT5 and GLUT2 primarily transport proteins. Our capacity for fructose absorption in each individual varies, but is often incomplete. So when someone consumes too much fructose, it exceeds their capacity for absorption in the small intestine, and the unabsorbed fructose travels to the colon. Here it is fermented by colonic bacteria, producing gas and fluid, leading to symptoms that are similar to that seen in lactose intolerance. While this is often labeled as dietary fructose intolerance, it is not a disease and should not be confused with hereditary fructose intolerance, which I will chat about in a moment. Fructose absorbed into the blood must travel first to the liver, where roughly 75% of the fructose is taken up by liver cells through a similar transport mechanism as with the intestine. The remainder then enters the systemic circulation, from which the kidney and small intestine absorb and metabolize the vast majority of what is remaining. Is fructose metabolized in these tissues? Starting with fructose, the enzyme fructokinase first catalyzes the phosphorylation of fructose to fructose 1-phosphate. From here, aldolase acts on fructose 1-phosphate to split it into DHAP, or dihydroxyacetone phosphate, and glyceraldehyde, or GA. Aldolase B is only found in the liver, kidney, and small intestine, as is triokinase, which catalyzes the phosphorylation of glyceraldehyde to glyceraldehyde 3-phosphate. From here, GA3P, or glyceraldehyde 3-phosphate, and DHAP are actually intermediates in the pathways of glucose metabolism. So fructose has the same metabolic fate when the pathway is running normally. GA3P can either undergo the final reactions of glycolysis to produce pyruvate, which is metabolized and then enters the Krebs cycle. Alternatively, it can undergo the aldolase-mediated reversible conversion of GA3P and DHAP to produce fructose 1,6-bisphosphate, which subsequently can complete gluconeogenesis and form glucose. Finally, shown here is the pathway for glycogen breakdown, or glycogenolysis, which is important in mobilizing glucose from the liver. Now you'll note here that aldolase has been mentioned twice now, with two separate reactions. The aldolase enzyme comes in 3 isoforms. Aldolase A and C are expressed in muscle and brain and catalyze the reversible cleavage of fructose 1,6-bisphosphate as one of the steps in gluconeogenesis and glycolysis. Aldolase B isoform is the one that we are more interested in today. It is limited to the liver, kidney, and small intestine, and it catalyzes both aldolase reactions. However, its role as a fructose 1-phosphate aldolase is, as shown here, is not duplicated in other tissues, and it will be of great interest as we move on to discuss hereditary fructose intolerance, which is an important disorder of fructose metabolism. Hereditary fructose intolerance, or HFI for short, occurs in approximately 1 in 20,000 individuals, and it is the result of mutations in the aldolase B gene, also known as ALDO-B, and this is on chromosome 9. More than 40 different disease-causing mutations have been identified, all of which result in a dysfunctional aldolase B protein whose enzymatic activity is reduced to less than 15% of normal values. So as a result of this, the clinical and biochemical manifestations of this condition result from acute or chronic exposure to fructose or sugars that are metabolized to fructose, such as sucrose or sorbitol. As mentioned, most of the issues in HFI relate to the resulting inability of the new altered aldolase B protein to cleave fructose 1-phosphate to DHAP and glyceraldehyde. So here's the crux of the problem. In that first fructokinase reaction in fructose metabolism, ATP is consumed. Aldolase B, cleavage of fructose 1-phosphate, is needed to produce DHAP and glyceraldehyde, which are intermediates that can enter the glycolytic pathway and will regenerate ATP and reclaim phosphate in the form of ATP. Now, unfortunately, in HFI, because of the loss of this enzyme function, phosphate becomes trapped in the fructose 1-phosphate substrate, which accumulates in the cell following fructose ingestion. This trapping takes phosphate out of the intracellular pool and leads to a net ATP consumption. Meanwhile, the deficient aldolase B can no longer condense the DHAP and glyceraldehyde 3-phosphate, which normally promotes endogenous glucose production through gluconeogenesis. The consequences all stem from these primary abnormalities. Let's now use this diagram to depict what goes wrong and what the consequences are. So first, hypophosphatemia occurs because the liver sequesters phosphate from the serum in an adaptation to the depletion of intracellular phosphate. Hypoglycemia, the other prominent feature following fructose ingestion, occurs because of the inhibition of gluconeogenesis and glycogenolysis. First, ATP and phosphate depletion impair glycogenolysis, which requires these substrates for its phosphorylation reactions to mobilize the glucose. Gluconeogenesis is inhibited because of the primary enzyme deficiency. Fructose 1-phosphate accumulation may also directly lead to inhibition of the enzymes in these pathways. As a result, hypoglycemia ensues as the liver cannot produce or mobilize glucose. When or if fructose is chronically ingested, the other consequence of this is that the liver ends up storing this excess glycogen, leading to hepatomegaly and steatosis within the liver cells. Now, intracellular depletion of ATP and phosphate also promotes AMP deaminase and other enzymes which are key in purine degradation, and this leads to increased production of uric acid. Hyperuricemia results, as well as increased urinary excretion of uric acid if this were to be measured. Further, magnesium, which is normally bound to intracellular ATP, now becomes released following ATP depletion, and this, in some situations, leads to hypermagnesemia. Further, ATP depletion also leads to a reduction in all the cellular processes within the affected tissues that cannot produce the aldolase B. And fructose 1-phosphate accumulates at what is thought to be toxic intracellular levels. The combination of these factors is thought to lead to cell necrosis in both the kidney and liver. The liver is often injured acutely, with serum aminotransferase levels often increased by more than twofold after fructose ingestion. Young infants often present acutely with liver impairment associated with a prolonged INR, edema, and conjugated hyperbilirubinemia, but acute liver failure is exceedingly rare. Liver disease can be progressive, however, as older infants and children can present after chronic fructose consumption with hepatomegaly and failure to thrive, and later chronic liver failure. Similarly, acute and or chronic renal disease have also been documented, specifically proximal tubular dysfunction. Usually this disturbance resolves when fructose intake stops. The same is true for the liver as long as the disease is caught early. And even following elimination of fructose, it appears as though hepatic steatosis and mild hepatomegaly may persist for a considerable period of time thereafter. Finally, fructose 1-phosphate accumulation produces a negative feedback on the enzyme fructokinase, resulting in a buildup of intracellular fructose. This limits hepatic fructose uptake because of the change in the concentration gradient, and this results in fructosemia, or high fructose in the blood, and fructosuria. That concludes the brief screencast. I hope this was helpful in explaining some of the concerns that arise and are noted in hereditary fructose intolerance.